All right. So, in this is just the actual beginning of this session. Okay. Now, in this session, we're going to look at the. I'm going to introduce electronics and embedded systems to you because the things that we'll be doing actually involves embedded systems, right? So, I'm going to quickly introduce it to you in this session, and then also again help you establish some foundation. Now, I'm going to use an analogy which I think has helped me over the years to understand electronics and embedded systems. Okay, so I'm hoping that it will help you too. All right, so let's get started. Now, when we talk of electronics, yes, the formal definition, we say that electronics is the physics. Please, can you see the slides?
Yeah, we can.
Okay, so we say that electronics is the field of physics and technology that deals with the behavior, flow, control of and applications of what electrons in materials, right? This is what we know, at least from our books. Okay, now usually it is about the movement. Okay, we are interested in about the movement of these electrons in materials and their application, the useful applications that we can make out of them. Okay, now let me ask you, how was your experience in electronics like when you were in school? Or let me put it like this: how have you been learning electronics so far? How have you been learning it? Anyone?
I experienced electronics so far.
Mm-hmm.
It hasn't been good.
Okay, so what has been the source of the challenges that you face?
They don't take their time to explain the concept,
Okay,
and we don't understand it. So moving on from it is hard.
I see. I see. That's fantastic. So actually, I've also had the same challenge previously, but then I had to persist through it. Okay, so that's why I like to organize this kind of trainings. Okay, now the question is that why would we like to study the behavior of these electrons in materials, right? The whole idea or the whole destination is for the purpose of applications, right? So that we can actually engineer devices and other stuff, other useful stuff from them. So right now, you realize that there are more electronic stuff around us than any other thing. Okay, so we say that electronics actually plays a pivotal role in modern society and technology. Now, think about what aspects of life can you say that it has not been touched by electronics? I mean, talk about communication, transportation, health. In fact, even religion, the way we worship. Now, just a while ago, we had this COVID incident, and we still had to worship. Okay, though we had to maintain social distance and all that, we still had to worship. And you realize that there was a boom in what we call the online meetings, right, where Zoom itself is part of the thing. Okay, so it's almost like right now there is nothing that we can do without electronics. In fact, electronics has become the core of almost all forms of technologies that you can think of, and in whatever field that you can think of. Okay, all right. Now, why is this the situation? The whole thing comes from the main thing that this electronics is built on, which is electrical energy. Okay, so let's look at some of the characteristics and advantages of electrical energy. If I should probably ask what forms of energies you know, you probably mention about sound, heat and all that, right? But why don't we use probably sound for these things that we do? But we are so much interested in electrical energy. And you realize that every country actually is interested in its electrical energy supply, right? Now, one of the characteristics that makes electrical energy so important is that it is fast, okay? The energy travels close to the speed of light, and we are talking about 300 million meters per second, right? So that means that it is easy to transmit this energy from one place to another. Okay, so Ghana, for instance, the Akosombo Dam is like 2 regions away from where I am right now. But then the moment that the switch is turned on, it's almost like a second, 2 seconds, the light reaches where I am, right? It's because of the speed of the energy. Now, sound typically would do like 340 meters per second in normal conditions, right? Now, this would take a lot of time to cover that same distance that light will travel, okay? Good. Now, the next thing is that it is transmittable. Okay, when you walk through town, you see these high tension cables. Okay, all that they are doing is transmitting the energy. So the fact that electricity or electric energy is fast and transmittable gives it or makes it ideal for the things that we do with technology right now. Okay, now these are not just the only things. It is silent too. Okay, just imagine your sockets or the cables running through your house were making noise. I mean, the house will be unbearable to stay, right? But then you realize that the energy is relatively silent. I mean, you can argue that when the energy, for instance, when we are transmitting alternating current at very high voltages, yes, you can hear some sound. But I mean, what we observe in our homes is quite silent, and I mean the mobile phones that we use, we don't hear any sound coming from the fact that it is discharging or using electricity. Okay, so this is also a very, very important. Now, another important thing is their storability. Okay, I don't know even if that's a word. Okay, the fact that they are storable. So batteries. What do we do with them? We just use batteries to store some of the energy so that we can use them outside. Okay, so through the application of batteries, or because of this characteristics of electricity that makes it storable, we're able to do portable devices. Is that okay? We can have our mobile phones go outside without connecting any cables to it. Okay, that would have been unbearable. Okay, so these are a few of them, and I think we can actually add more. They're also convertible. Right now, it's almost like electricity is central, right? You can convert electricity to almost any form of energy, okay, using actually transducers. Okay, so if I want to produce sound, I can just use a speaker to do that. If I want to produce motion, I can use a motor to do that. If I want to produce heat, I can use a heating element to do that. Okay, so it is easy to convert electricity from into other forms of energy. Okay, it is much easy and convenient, and it is also controllable. In fact, the whole idea of electronics is so that we'll be able to control and manipulate the energy. Is that okay? It is not very simple with other forms of energy, okay, but electricity, it is highly controllable. Okay, now this, I just want you to put somewhere in your mind. Okay, now let's also quickly look at embedded systems. If I may ask, what do you know about embedded systems? If you've heard of it before, what was the topic from which it was being discussed? Okay, or where did you see it? Did you learn about it from school? Yeah, anyone? Embedded systems, what do you know about it?
Well, from what I heard from school was embedded systems has to do with bringing computing power to regular items. So it's more like
Exactly.
embedding, yeah, the computer into
Exactly.
regular items, something like that.
Okay. So In simple terms, embedded systems are typically specialized computer systems, okay, that are dedicated to perform a specific function in another system, okay. So it could mostly be in the form of it's extending a hardware environment or even a software environment, okay. There are situations where I had to design a software, but then I had to also build an embedded system client for it to communicate with that software, okay. So it can be used within an extended or to extend a hardware function or even in a software environment, okay. Now, one of the uses that we use, or the applications, is usually for control, for monitoring, for interaction. Now, take a vehicle for instance, right? Vehicle by default is a mechanical system, but right now you realize that there are more electronic components in vehicles, and it even keeps increasing, right? To the extent that they are now even converting it to purely electrical in nature. But then, that aside, you realize that the dashboard and the control, so there are some control units that run embedded systems applications to do particular things, okay, like your fuel gauges, your locking systems and all that, okay, tire pressure recorders. So all these things are embedded systems that have been incorporated into the car to extend its abilities and or its functions, also making it easy to use, okay. Now, usually when I talk about embedded systems, I like to compare it with the human system, the human body, okay, because it looks like conceptually we can model the human body as an embedded system, right? If we use the right perspective, okay. Now, I should probably put out that the human system is actually very complex, okay. It's a complex biological system, but then we are just trying to zoom in. I'm just trying to zoom in on certain aspects that actually have their analogous, or that relates or corresponds to how embedded systems actually work, okay. And for me, using the human body as an analogy to explain embedded systems really helped me to understand things, because there are situations where when I need an idea, I just focus, okay, how would the body perform such a thing, and then get into a little bit of biology and I get an idea, okay. So let's look at a typical scenario. So there is this patient who has a problem with the knee, okay. So the doctor hits somewhere on his knee, and quickly his leg jerks, okay. Now you realize that when whatever happens here, for information traveling from the legs to the brain and back to the legs, is actually similar to the things that we do when we build embedded systems, okay. So let us actually look at that, okay. Now, if you take the human body, we have 5 sense organs, okay. We have 5 sense organs. Jokingly, there are some people with the 6th sense organ, okay, those who have sense of humor, okay. But that was just a joke. Now, what is the importance of these sense organs? Okay, very, very important. Why do we need these sense organs? So the sense organs actually serve as the interface to our brain, okay. The rest of our bodies actually, the rest of our bodies are able to cause the brain to perform an action through these sense organs. Very, very important. Now, they also serve as a means to which we interface with our environment. So take it as you get to an environment and the place is warm, your skin actually detects it, sends information to your brain, and then at that point you can take a decision, right? Or you go somewhere, the place is dark, your eyes sense it, take it to your brain, and then you can make a decision of finding a light source, okay. So the senses actually help us to interface with the environment. So think about a scenario where there is a human being without any of these senses, okay, that person will be completely dumb, because the person will see fire and will walk into it. Okay, he won't even see in the first place. A lion will be barking and roaring and coming, and he will just be there. Okay, so with these senses, we become aware of our environment and we're able to make decisions based on the signals or the stimuli that we get from our senses. Okay, and through these senses, our brain is able to get data to interact with our environment and also help us to make decisions. Okay, now in biology there is this thing called accommodation. Okay, have you realized that when you are in a room and all of a sudden the lights go off, you can't see, but give yourselves a few seconds and then you can now see, right? Yeah, so we call it accommodation. Yeah, the ability for your pupil to adjust itself to see different light intensities, right? So these are some of the things that the senses do for the brain. Okay, it gives the brain data, then the brain in turn performs a decision or regulates an action. So if you take a typical nervous activity, okay, if you consider a typical nervous activity, so let's say that you see an apple, right? Now you see with your eye, so the sensor that actually plays a role here would be your eye, which in biological terms we call it the receptor, right? So the stimulus is seen by the eye, the video, the visuals is seen by the eye. Now what the eye does is it converts these signals, visual signals, into electrical pulses. Now this is actually interesting. The signals that flow to the brain, they're actually electrical in nature, okay, and they flow through your nerves, okay, your neurons. Now there are two things that can happen. Depending on the nature of the signal, the stimulus will go through what we call the reflex arc or the the medulla oblongata, which is also part of the brain, okay, and the medulla oblongata is actually responsible for autonomous activities or involuntary activities, if I may put it. Or it may go to the brain where you have to actually make a conscious decision. Now let's look at a situation where you are walking somewhere and unknowingly you step on a nail, right? You see that your body actually performs the necessary actions required to take your leg from the nail before your attention even comes onto the fact that you have stepped on the nail. Now these are some of the biological features that helps the human body to protect itself, right? Then there are things that, yes, you have to deliberately think about the decision. For instance, okay, the weather is cold, what do I do? Okay, let me switch on the heater in the room, or if I don't have a heater, then let me get more pullovers. In this case, you are thinking about what you are doing. Now I need you to follow this carefully, okay? Usually when we start teaching electronics from this perspective, people are in a rush to do the actual electronics thing, but trust me, from experience, pay attention to these things and make sure you have a very solid understanding. Once we get to those things, you realize that all these things will come in very handy, okay? Now, in biology or in engineering, there is actually a concept called biomimetics or biomimicry, where we actually study nature and look at how nature is actually solving a particular problem and we try to mimic it, right? So for instance, aeroplanes were built based on studies from pigeon, right? The helicopter from the dragonfly, the submarine from the ship and all that, okay? There are a lot of engineering marvel that they took inspiration from nature, okay? We call it biomimicry, and personally I use it very much when I'm building systems, okay? Now if we look at the equivalent embedded system, you realize that if we put this on side by side with our nervous system or the central nervous system, they share some similarities, right? So for embedded systems, we have electronic sensors, unlike the human body where we have biological sensors. Now, these sensors usually pick data, so we are looking at light intensity, sound, and all that, okay? So whatever sensor that you are using, Now, usually the sensors actually output their data in the form of analog signals, okay? So we need something to convert them into digital form. Digital, by the way, means that the signal can be a string of zeros and ones, okay? We convert the analog value, which is continuous. So an analog value could, if let's say it's ranging from 0 up to 5, it could have we could have a values like 2.5, 3.3, 1.2, okay? But then when we digitize it, then the values now become restricted between just 2.1 or 0. Is that okay? So that is what this analog to digital converter does. It converts the analog signals from the sensor into digital form. Now, why does it have to do this? This is because the computing unit which we use in embedded systems can only process digital signals, okay? Now, there are a few sensors that actually have digital output. So in that case, you don't need to connect them to, you don't need an ADC to connect them to the CPU. You can directly connect them to the CPU. So take notice of all these variations that we are looking at, okay? Right, so the moment, as soon as the ADC is done, it sends the information to the central processing unit, okay? Now, the central processing unit will now perform a decision or an action based on the software or the firmware that we've put onto it, okay? So you realize that here it is serving as the brain, okay? So when we detect that, okay, the weather is cold, based on a past experience, what we learned to do when the weather is cold, we do that thing, okay? So the same way, this central processing unit cannot do anything unless we specifically tell it what to do, and we instruct it using software, okay, which is something that we'll be doing in the second training session of this particular series, okay? Now, once the processor is done, it has to perform an action mostly, okay? Now, the action that it has to perform, remember that the data on the CPU is now digitized, but mostly the things that have to perform the action require analog data. So that means we have to reverse the activity of the ADC using another device called DAC, digital to analog converter. So this guy converted analog to digital. This will convert the digital to analog, pass it to something called actuators. Actuators are usually things that are able to perform an action, okay? Something like a motor, yeah, so something that we can use to trigger an action, okay? And the cycle continues in that way, okay? So if we look critically and put embedded systems and the human nervous systems together, they share some similarities, which as an electronics systems designer, you could pick a lot of inspiration from. So I'm just going to touch on a few of them, and then we would continue with what we want to do. So let's start with the first one, the sensors, right? So for the human body, five biological sensors, and fortunately we can use these sensors. I mean, these are all that we need, right? Your eyes alone can perform many things. It can see color, it can see light, it can sense motion. In fact, it can do many things. Now, just the eye alone, you will require you to use a lot of electronic sensors, okay? So in terms of the biological sensors, yes, we also have electronic sensors for the embedded system, okay? Then when the signals are generated, these signals have to travel. In terms of the human body, these signals travel through what we call the nerves or the neurons, okay? But for embedded systems, our neurons become our wires, our trace, PCB traces, and all those stuff, right? Yes, so as I said earlier, these things actually do share some similarities, and once you understand it, you realize that it is actually something interesting. Then in the body, we have muscles to perform actions, right? So if, for instance, you touch something that is hot, your hands have to move, okay, move away. And then similarly in embedded systems, probably we want to lock a gate, we want to open something, okay, we have this kind of what we call actuators and effectors to perform those actions, okay, relays, contactors, and all that, okay. Yeah, so I hope you guys are seeing the correspondence, the correlation between these two fields, right? Then finally, one thing that we can never leave out is the brain, okay, where everything is processed. So in our embedded systems, the brains that we'll be using are what we call the microcontrollers. Is that okay? And for this particular training, we'll be using the Atmega 328 microcontroller together with the ESP32 microcontroller. And the whole idea of using these two microcontrollers together, although I could just use one of them, is for the purpose of the teacher. Is that okay? So the microcontrollers are going to be the brains of our embedded systems where we will make all the decisions. Okay, so very, very interesting stuff. Okay, very, very interesting. So in simple terms, if I'm to summarize embedded systems, I would probably say that it's a smart decision making device that interacts with the world, take actions, communicate based on the tasks that it has been designed for. Now as I progress with the PowerPoint, don't worry, you're not going to be using PowerPoints throughout. This is not going to be a lecture, a university type lecture, just using PowerPoint to convey a few information, and we'll switch to actual hands-on stuff. Okay, all right, so that is it. Just a little things I need you to know about embedded systems and about electronics. Now trust me, if you want to take the whole embedded systems, it's a whole course on its own. Okay, so this was just to give you an understanding of what I mean when I talk about embedded systems and electronics. Okay, all right. Okay, so right now we're going to look at, we're going to zoom in directly into the basics of electronics, okay? But then, one question I want to ask, why do we even want to do electronics? What's the whole purpose of doing electronics, right? We previously defined the fact that electronics is the study of the movement of electrons, their manipulation. But the question is, why do we want to do all this? Is that okay? So I want to quickly talk about what is the fundamental aim of an electronic systems designer. Okay, if you call yourself an electronics engineer, what is basically what will you be doing all the time? Okay, now you could be working on communication systems, medical imaging systems, rockets, whatever it is, but basically at the fundamental point of it all electronic, all of us, no matter what you are doing, will be doing a common thing. Is that okay? And that's what I want us to quickly look at. Okay, what we do as electronic systems design. Okay, now please, I need you to pay attention to this, okay? So basically, okay, when we say somebody is an electronic systems designer, is the job is simple, okay? We have some electric load, and in this sense, when I talk about electric load, I'll be referring to any appliance that has the ability to consume electrical energy. Is that okay? So let's take the light bulb for instance, okay? Now, there is also, we want to move energy from this electric energy source, which could be a battery, right, to the load so that this light bulb can turn on. Basically, that is what we want to do as electronic systems designer, okay? So now, how do we do that? How do we move this energy from the source to the load? Okay, now there are some important questions that we need to ask first. Now, the first one that I think is, how much energy should be delivered to the load? Okay, how much of this energy are we trying to deliver? Because let me use an analogy. Let's say that I ask you to, if I should ask you that, get me water, right? There is a question that you should probably ask me. What question do you think you should ask me if I just say, get me water? What question would you ask? Yes, anyone? Assuming I just call you, get me water. You should ask a question. What question do you think you have to ask?
Yeah, it's a glass or it's a bucket or how much you want.
Fantastic. So you have to actually ask about what I want to do with the water, right? Because if you don't ask and you bring a bucket of water, meanwhile I needed a cup of water, then something is wrong, right? So if I ask you for water, you have to actually ask what the purpose of that water. So if I say, okay, for drinking, then you won't bring me a bucket of water. As a matter of fact, if I say bring me water to drink and you bring me a bucket of water, there is something wrong with you. Right? So if I ask for water to drink, you're going to bring me a cup of or a glass of water. If I want water to bath, you won't bring me a glass of water, you would bring me a bucket of water. Okay, so how much water you would bring to me depends on the purpose of the water. Is that okay? The intended purpose of the water. The same way, how much of the energy we want to move from the energy source to the load depends on the load's requirement. It is the load that actually dictates what goes on in a circuit. Is that okay? Now the next question that I think you should ask is, when should the energy be delivered to the load? Now this is very important. Okay, so in our situation we are even using a light bulb, right? A light bulb is only required when the place is dark. You don't switch on a light bulb when you are standing in the sun. That's madness, right? So there is always the question of when the energy is supposed to be delivered, okay? Then we can also ask the question of how frequently should the energy be delivered, because there are situations where you need the energy to be delivered in pulses. Take it as a car's traffic indicator, right? When a driver wants to negotiate a curve, he turns on the traffic indicator and you see that it begins to what? Blink. Take traffic light for instance. At a point we have green light for one direction, at another point we have green light for another. So there is the parameter of timing, okay? The parameter of timing. And then what are the specific constraints or standards that it should adhere to? Now, this is one of the most important questions as a circuit designer or as an engineer you should ask yourself all the time, okay? Else you will build systems that nobody would actually patronize. Okay, you build systems nobody would actually patronize your system, because take for instance, assuming your mobile phone didn't have battery, you always have to connect a cable to it. You can't. It would just not be interesting to use, right? And assuming you have to charge your mobile phone every 1 hour. That will also not be ideal. So as a system designer who is working on a mobile phone, one of the things you have to look at is to make sure that your system is efficiently dependent or is able to efficiently depend on battery for a very long period of time. So these are all what specific constraints. And there are also the question of standards. Every country has certain standards that electronic systems have to meet in order to be accepted. Okay, so you cannot just go about creating your own thing, not minding anyone. Everything that you create has to fit. So if I'm designing for, let's say, US, I have to make sure that my system obeys the standards that they require, else nobody is going to, else it will not be allowed in the first place, okay? And you would have done a cost 90 job. So let's take these questions one after the other and see how important they are, okay? Now, so the question about how much energy should be delivered, okay, how much energy should be delivered. Now, the first thing is that it mainly depends, like I said earlier, the amount of energy that needs to be delivered is decided by the load. Is that okay? So if my light bulb is, let's say, 9 watts, 9 volts, right, then the circuit that I'm building should be a circuit that will be able to transmit 9 watts of energy from the battery source or from the power source to the load. Is that okay? That means I can't do anything else apart from this. So your load dictates what your circuit has to be. Is that okay? Then another thing is to what we call it is in DC, or when you are working with DC, that is direct current or low frequency circuit. Okay, you have to also ensure that the voltage is correct, the level of the voltage. So for instance, if the lamp is 9 volts, your circuit conveniently supplies this 9 volt, because if you supply less than that, your device may end up not working. Okay, and you supply more than that to your device, will end up not working. So you have to make sure that the circuit that you design meets the voltage requirement. Is that okay? Another thing too you have to make sure is that when the voltage is intact, is your power source or is your circuit able to deliver the required amount of current that the system needs. Okay, so these are two very, very important things. These are two very, very important things. Now, in case your energy source is unable to meet your voltage requirement, this is what is going to happen. Let's say that I have a power source, a battery that is rated 9 volts, half of an amp, 0.5 amp, right? And I'm trying to use it to power a bulb, a light bulb that is 9 volts, 1 amp. Okay, you see, the voltage matches all right, but then the current doesn't match, and this is going to be an issue. Okay, for the bulb to perfectly work, you need the battery to be able to supply the voltage and the current. Now, when you connect in a situation where the battery or your power source cannot deliver the required current, when you connect the load, which is the light, to the lamp, the battery, what you would see is that the voltage is going to drop. Okay, there is going to be a reduction in the voltage. This would happen because the system will try to balance to raise the current that the system the load needs, and in so doing, it has to compromise on the level of the voltage, because in the end, power has to be unity. Okay, the input power has to be equal to the output power. Is that okay? So if you probably have a power supply that you can regulate its current, try what I'm saying and see. Find a device that probably uses, let's say, 9 volts, 1 amp, and set your power supply to 9 volts and 500 milliamps, right? You realize that the voltage will drop. Okay, that is what is going to happen, because the system tries to raise the current, but by doing so, it's going to compromise on the voltage that it is it is using to it is delivering to your system. Is that okay? Now, another thing is that your energy source, okay, and here if I talk about energy source, I'm looking at the batteries and more. When it comes to voltage, your energy source, the voltage from the energy source has to be able to meet the exact voltage requirements of your load, right? But when it comes to current, one thing I need you to put in your head right now is that every device, the moment the voltage matches, you don't have to worry about the current, because the device is going to pull the current that it needs. You don't have, in fact, when you are building circuit, you could just focus on making sure the right voltages appear at the right places. The system will regulate the current on its own. Now, it only becomes an issue when the current is not enough, it's not up to what the device requires, right? So that is to say that if, let's say, I want to power a 9 volts, I want to power a 9-volt lamp, which requires 1 amp of current, I could actually connect it to a power source that can deliver 9 volts and even 1 million amps. Still, the load is just going to pull that 1 amp that it needs. It is never going to pull more than. The moment you see that the load is pulling more than that, then it means something is wrong. Is that okay? So whenever you are building electronic systems, just make sure your voltages match, and for the current, make sure you have enough for the system. Now, allow the system, it will pull the current it needs on its own. You don't have to worry about that. Is that okay? That's why we are mostly talking about voltage regulation, voltage regulation, voltage regulation. That is the situation. Is that okay? So, like I said, when you connect systems, you should rather have a system that has a higher current carrying capacity. Your power source should be able to deliver a higher current capacity, okay? But for the voltage, you should always make sure that the voltage is matched. Now, later in the next sessions, I would explain why this is the situation. Is that okay? Okay. Now, still on the question of how much energy should be delivered to the load. Okay, so I already explained that when all you have to do is to make sure your voltage matches the load's requirement. For the current, you need the current to be at least what the load requires. You shouldn't worry about the system being able to provide more current than you need. You should rather be worried about the system not able to meet your current requirement, because it is in that situation where it will have to compromise and cause a drop in your voltage. Is that okay? But like I said, so far as your voltage matches and your system can deliver the current that is required, you can just ignore everything else. Is that okay? Very, very important. So in cases where your voltage is either higher or lower than what the load, then we will need additional circuitry to step down. So we will step down if the voltage is higher, or we step up if the voltage is lower, okay, until we meet the requirement. Now, you see, we are not just interested in moving the energy, okay? Another thing that we have to also make sure as circuit designers is that the energy is moved efficiently. If we end up wasting the energy in the circuit, that means if the system that we are building is battery powered, then our battery will drain faster. Is that okay? So as circuit designers, as we are building the circuit to move the load, we have to make sure we cut down on losses, okay? So efficient energy delivery is very, very important, okay? So in a sense, the electric load or whatever appliance you are trying to build the circuit for will determine the amount of work that the designer has to do. Okay, now the PowerPoint I'll share with you later, because I actually made it as notes. So if you are probably reading it, you realize that it's basically everything I have to say. Okay, so I'll share them with you so that you can use them as your guidelines whenever you want to, something is not clear. Okay. All right. Now the next question that I want us to look at is, when should the energy be delivered to the load? Is that okay? When should the... Now, it could be as simple as, okay, when we press on a switch. Is that okay? So, for instance, right now in my room, okay, if the place, if I think the place is dark, I press on the switch. Okay, so that means that the load will not always be receiving the energy until the load will receive energy only when the switch is pressed. Okay. Now, this thing can also be as complex as... It could be a very complex system. Okay, so typically we could have the control or the instruction coming from a mobile phone through some IoT network, through some systems of Wi-Fi, relay connections, and all that. Okay, which is actually something we'll be building. We'll be building something similar. Okay, so it could be very complex. Okay, depending on the intended purpose of the circuit. Yeah, it could be maybe when I press a button on my phone, then the system turns on, or when the sun's intensity goes below a certain limit, my outside lights should turn on, and all that. Okay, so how the energy gets delivered could actually be very, very complex. And as a circuit designer, All these things you have to pay attention to and you have to consider them. Okay, remember, your job is to fulfill what your client wants. Is that okay? So if these are the client, no matter how complex your client's requirements are, you as the circuit designer, you have to make sure that you are fulfilling those needs. Okay, now the next thing that I want to talk about is the frequency at which we want to just a second.